All right, we're going to look at number 26 in section 5.1, which asks us to find a formula for R sub n. So this is the right-hand approximation, right, with n subintervals. They use capital N. I'm going to use lowercase n. Just whatever you use, just be consistent with that. So find a formula for that, and then we're going to compute the area under the graph of this function over this interval as a limit. So we're going to find the right-hand sum approximation for this function over this interval, and then we're going to take the limit basically as n goes to infinity, right? That becomes the area under the curve. So you could graph this function if you wanted to and see what it looks like over that interval. It is indeed positive above the x-axis over this interval. So we're going to find that area under the curve. Okay, so just to reiterate, here's my function. Interval is going from 6 to 11. So remember, we usually talk about going from A to B. A is 6, B is 11. And the width of each of our n subintervals then is B minus A over n. All right, again, I'm using lowercase n instead of capital N. So that's going to be 5 over n when we calculate that. The right-hand endpoints, if you remember, I'll call those C sub I, are A plus I delta x. So A is equal to 6. And of course, I times 5 over n is 5i over n. And so here's my right-hand sum approximation for each subinterval. And the height of the rectangle by the right-hand endpoint, so that's f of ci, and multiply it times the width, which is delta x. So I've got f of ci, which is this, times delta x, which we computed to be 5 over n, excuse me, 5 over n. So I need to evaluate this, right, which means plug it into this function. So I'm going to replace x with 6 plus 5i over n, and therefore I'm going to get 11 x squared, so 6 plus 5i over n squared, plus 77 times x. Again, x is 6 plus 5i over n, and don't forget our delta x out here. Now, be careful, if I square this, be careful that the inner and outer, right, I'm going to get first times first 36. The inner and outer is 30i over n, so I get 60i over n when I add those together, and then the last times last 25i squared over n squared. So make sure you FOIL that out. And then to clean this up, I'm going to distribute this 11 right here through each of these. So 11 times 36 is 396. 11 times 60i over n is 660i over n. And 11 times 25 I squared over n squared is 275 I squared over n squared. And then I multiply 77 times 6, do the distributive property here, and 77 times 5i over n. Okay. Having a calculator may be helpful if you're having trouble multiplying those kind of somewhat big numbers. Now I have this delta x. Don't forget, sometimes students I see will all of a sudden it just disappears. Don't forget, we still have it. You could factor it out as a constant multiple using the linearity properties of summation. I'm going to choose to leave it in here, and I'm going to distribute it through here. But before I do that, let's combine like terms, right? What's 396 plus 462? Well, it's 858. And notice these two have a common denominator of n, so 660i plus 385i is 1045i over n, and then I have this one. So just simplify, makes it a little bit easier. That way you don't have a bunch of sums when you look at the power sums later. Now I'll finally distribute one more time. So we're using the distributive property like crazy here over these. So 5 over n times 858 is this big number over n. 5 over n times this is 5225i. Notice it's over n squared. N times n is n squared. And then this times this gives me this fraction. And notice again, n times n squared is n cubed in the bottom here. Okay. So now I'll use the linearity properties. I'll rewrite this sum as as 3 different sums, right? I'll break it up into those 3 different sums. Okay. And then just looking at this one, there's no variable here. There's no I. This is a constant, 4,290 over n, and I'm adding it up n times. So anytime you're doing a constant from I equal 1 to n, it's just the constant times n, right? So I'm just going to rewrite it that way. So we've evaluated that sum. Here, I'm just going to take use the area properties, the constant multiple of 5,225 over n squared. I'm going to factor that out, leaving just the I. And here I'll factor out the 1375 over n cubed, leaving the I squared. Okay, it's a long problem. We go to page 2. And in page 2, I will now replace these with the appropriate power sum formula. So on the test, I will have available these power sum formulas. So notice we have the summation I equals 1 to n of I. And I'm going to use the far right. It's the way I like to do it. This makes it easy, I think. And then for the summation equal 1 to I squared, I'm going to use again this far right expanded form. So that's what I've done for the summation I equal 1 to n of I. I've replaced it with n squared over 2 plus n over 2. And then the summation I equal 1 to n of I squared, I've replaced right with this right here. Okay. So then we will now do what? Another distribution, right? Distribute here, and simplify those corresponding fractions. So here I'll get, notice the n squareds will cancel. I'll just get 5,005 over 2. Here, one of the n's will cancel, so I'll have a 2n down there, 5225 in the top. Multiplying these two, the n cubes cancel, and I get 1375 divided by 3. And then here, times here, 1n will be left in the denominator. I'll get 1375 over 2n. And then here, 1n, n cubed, I'll have n squared in the bottom, 1365 over 6n squared. So here's the sum. And I'm not going to simplify this by combining any like terms. I'm just going to go right to, this is R sub n. What they really want you to do is to, find the limit, rather, of this as n goes to infinity. So as n goes to infinity, what's happening to our R sub n? Well, this term, the first term, this second term, and this term over here, they're all constants. There's no n at all in them, so they're just going to stay the same. But look at these three fractions with the variable n or n squared in them. As n goes to infinity, right, this thing is going to 0, right, as n goes to infinity. And similarly, these two also will go to 0, right? Because the denominators will grow without bound, making that fraction closer and closer to 0. So literally all we're left with are these constant terms. If I add them all up, they do want you to put it in symbolic notation and fraction forms where needed, these parenthetical instructions. Right? So we have to do that. And so I found the common denominator of 6, added them up, and I got my result. Here I approximated it here as well, but this is the one you want to enter in. No commas there again for the 44,165. Just put 44165 over 6 using the tool in Achieve. Okay, this was quite a long one, but I hope that is helpful.